This will be the last of our circuit videos, and it's chapter 18 in your textbook. We are going to be working with combination circuits. So we've already worked with parallel, we've already worked with series, now we're going to put them all together. And this one is more complex. So this is what you should be able to get out of this PowerPoint. You should be able to define a combination circuit, list the rules and the relationships in parallel circuits and in series circuits, and then we're going to solve a combination circuit and find its voltage, current, and resistance, and if we're really good, power also. Okay, so when we have a combination circuit, there's basically a mixture of series and parallel circuits. And the way we're going to know the difference is when we have a node is where we have a branch. That's kind of where it's coming in and then it branches off. There's the node right there. So your current comes in here and it has a choice of going in this direction or it has a choice in going in that direction. And then in a combination circuit, when the total power, the power of the whole thing is the sum of each resistor's power. So you can kind of know if you've done it all correct if you take up all the powers and then calculate the power from the battery. Okay, so this is a combination circuit. This one's not too complicated. The one in your practice C is more complicated than this. We have R1, which is our first resistor, R2, our second resistor, and R3, our third resistor. And if you look carefully, you'll see that right here we have a node. That's where the current has a choice of which way to go. It can go that way or it can go that way. And we have the current has no choice. It has to go through that one. So this guy is in series with these two. These two are in parallel with each other. They're in parallel because the current has a choice. It can go across the top or it can go across the bottom. So just a guideline, in a series circuit, your current is the same everywhere. So no matter what, you have the same current through each resistor. Your equivalent resistance, this is what we did before in our practice problems, is the sum of all the resistors, and our voltages will add up to the voltage source. In a parallel circuit, our voltage is the same everywhere, and the current through the branches add up. So if you look at the parallel versus the circuit, these two here, these two ideas here, voltage and current, are flip-flopped. In a series circuit, the voltages add up and the currents are the same. And then in a parallel circuit, the voltages are the same and the currents add up. But our equivalent resistance, we did this before, is 1 over R EQ equals 1 over R1 plus 1 over R2 plus 1 over R3 until we run out of resistors. So when we have a complex circuit, we have a whole bunch of different resistors like we saw in the previous video. We have some in series, they can be combined. We have some in parallel, they can be combined. And then we're just going to put them all together until we get one simple circuit that only has one resistor in it. So this is what we're looking for when we're done. Okay, so this is a different combination circuit. We have a battery, and our battery has there's R1 and R2, there's R3 and R4. So here's R1, that's this one, here's R2, that's that one, R3 and R4. So when you're looking at this, you kind of ask yourself, okay, is there anything that's obviously series or obviously in parallel? When we look at this circuit, we see that R1 and R2 are in series. The current has to go through these two. When it goes here, here's our node. Now it has a choice. It can go this way or it can go this way. But once it's in this branch, it has to go through both of these. So R1 and R2 are in series, And the same thing if we're the current, R3 and R4 are also in series. Since they're in series, the way you find the series resistance is you add the two resistances. So we're going to add 325 and 275, and that's going to give us the equivalent resistance for these two together. And then we're going to add 150 and 250, and that's going to give us the equivalent resistance for these two together. So R1 and R2 together will be 600 ohms. That's the 325 plus the 275. That's 600 ohms. R3 and R4 together will be 400 ohms. That's our 150 ohms and our 250 ohms, which is 400 ohms. Okay, so there's R1 and 2. It's all combined together, 600 ohms. R3 and 4, 400 ohms. These guys are in parallel because the current has a choice of which direction to go. The current can go this way, or it can go this way. When it hits the node, it has a choice of which way to go. So these guys are in parallel, and when we find their equivalent resistance, we're going to use 1 over 600, the 600, 1 over 400, add those together. That gives us 1 over REQ, and it comes out to 0.004167. And so take the reciprocal of that, and the equivalent resistance is 240. One of the ways you know you've done this right is your equivalent resistance should be less than either of your two resistors. Okay, so now we've redrawn that. We took the 600 and the other one, and we made one resistor, and our total resistance is 240 ohms. Not watts, it's ohms. So here's a recap of what we did. We put R1 and R2 together. These are ohms. The Greek letter ohms is a W, so that's the program went and changed those into W's. Those are ohms. R1 and R2 became 600 ohms. These were in series with each other, so we added them. So this is 600 ohms, 400 ohms, and then these guys are in parallel with each other, so that became the 240 ohms of our equivalent resistance of our simplified circuit. Okay, so now that we've got it all boiled down into one resistor, we can find the current that leaves the battery. So we use V equals IR, our Ohm's law equation, V equals IR, and we know that it's 240 volts. That's what we were given, that the battery was 200 volts. Our equivalent resistance is 240 ohms, so V equals IR, our current coming out of the battery is 1 amp. Okay, so now we're working in reverse. So we're going to go from the simplified circuit to the more complex circuit. We know that the current going from here is 1 amp. And then when it gets to this spot here, it's going to split. So some of it's going to go this way, and some of it is going to go this way. But these two here are in parallel with each other. Since they're in parallel with each other, the voltages are the same. So if the battery is 240 volts, this is 240 volts, and this is 240 volts. So now what we know is we know the voltage going through the first branch here, first branch, and we know the resistance of the first branch, so we can do V equals IR, and we can do voltage. 240 volts is equal to the current times 600. Same thing with the other side, we can do the same thing. And then we find out that, look, our 0.4 amps and our 0.6 amps adds up to the 1 amp that came out of the battery. So 1 amp came out of the battery, 0.4 amps went this way, and 0.6 amps went that way. Okay. Okay, so now we're back to the original circuit. We know now that 0.6 amps goes this way, 0.4 amps goes this way, so this 0.4 amps goes through both this resistor and this resistor because they're in series. They make it one loop, and the current does not have a choice which way to go. So now, again, we can use V equals IR, our favorite calculation, and now we're looking for the voltage through the first one, the voltage through the second one. We know the current, we know the resistance, so current times resistance equals voltage, current times resistance equals voltage, current times resistance equals voltage, and we can get all of the voltages that in each branch. So when we do the V equals IR, we find 130 volts for V1, 110 volts for V2, 90 volts for V3, and 150 volts for V4. Now notice that this 130 volts and this 110 volts adds up to the 240 volts we said this was. The 90 volts here and the 150 volts here adds up to the 240 volts that we said was in this branch. So that voltage equals the total voltage here and the total voltage there. Okay, so for a total review, we know that the current is the same through any point in our circuit. So see, through this branch, 0.4 amps, 0.4 amps. Through this branch, these guys are in series, 0.6 amps, 0.6 amps. And their voltage is equal to the sum of the voltage drop across the components. So 130 and 110 is 240, 90 and 150 is 240. And for parallel circuits, our voltages are the same. So the voltage across this branch was 240, 240, and that equals the 240 from the battery. But the current splits up. So the current, okay, our 0.4 amps through here and our 0.6 amps here add up to the 1 amp coming out of the battery. So if we went and calculated P equals IV, that's how we're going to get our power. And that's the current times the voltage. If we went and did this for each resistor and then went and did it for the battery, we would find that the P for the battery would equal to the power from 1 plus the power from 2 plus the power from 3 plus the power from 4. So when you do a combination circuit, you're going to simplify it as much as you can, reduce it down as much as you can, and you're going to redraw it until you get to one resistor. So you're going to go from the complex to the simple, and then work your way back up from the simple to the more complex until you get all your values. And anytime you have two values of V, I, or R, you can find the missing value.